This presentation introduces the holistic informational quantum field, abbreviated as HIQF. HIQF proposes that reality is not fundamentally composed of matter or energy. Instead, it emerges from a deeper informational field, where physical phenomena arise as structured projections of relational and dynamic information. Within this framework, space-time, energy, and matter are not primary entities. They appear as successive manifestations of the same underlying informational substrate, governed by changes in informational density and relational asymmetry. The purpose of HIQF is not to replace existing physical theories, but to extend them by addressing domains where current models face persistent inconsistencies, particularly in cosmology. By treating reality as an emergent informational process, HIQF offers a unified conceptual basis for understanding dark matter, dark energy, and large-scale cosmic anomalies within a single coherent framework. Modern cosmology is currently facing a structural impasse. According to the standard LCDM model, only about 5% of the universe consists of ordinary baryonic matter. The remaining 95% belongs to the so-called dark sector, whose physical nature remains unknown. This is not a minor gap. It represents a fundamental limitation, where the model successfully describes the dynamics of cosmic evolution, yet fails to explain the actual composition of reality. Several persistent anomalies highlight this tension. One of the most prominent is the Hubble tension, where measurements of the expansion rate derived from the early universe, using the cosmic microwave background, differ significantly from late-time measurements based on supernova observations. Additional challenges arise from recent observations by the James Webb Space Telescope, which reveal massive, well-structured galaxies forming far earlier than LCDM allows. Finally, decades of experimental searches have failed to directly detect any dark matter particles. Together, these issues suggest that we may be missing not a parameter, but an entire foundational layer of reality. This slide highlights a fundamental shift in perspective. In the current paradigm of physics, reality is described in terms of particles and fields embedded in spacetime. These entities are treated as primary, and their interactions are modeled within a fixed geometric background. The HIQF paradigm departs from this view. Here, the fundamental unit is not a particle, nor a classical field, but the information quantum, or IQ. An information quantum is not a bit of stored data. It represents a manifested duality of relation and effect within an underlying informational substrate. From this perspective, reality itself is a projection. Matter, energy, and space do not exist independently. They emerge as observable properties when symmetry within the informational field is locally broken. This leads to the central axiom of HIQF. All objectively detectable phenomena arise from specific perturbations of the same informational substrate. What changes is not the substance of reality, but the way information organizes, propagates, and stabilizes into observable structures. At the foundation of the HIQF framework lies the concept of a perfectly symmetric ground state. This state is defined as inactive potential, denoted by RQ, where the net informational perturbation is exactly zero. In this condition, no physical reality is manifested. There is no space, no time, and no matter in the conventional sense. What exists instead is a multidimensional informational field in complete internal balance. The expression delta E equals zero does not represent emptiness, but equilibrium. All relational interactions are present, yet they cancel each other perfectly, producing no observable effect. As long as this symmetry is preserved, reality remains unexpressed. Nothing evolves, nothing propagates, and no structure can form. This symmetric ground state is not a temporal beginning, but a logical one. It defines the baseline from which all subsequent manifestations arise once symmetry is locally or globally broken. Reality begins to manifest when symmetry is no longer perfectly preserved. This process is described in HIQF as symmetry violation, denoted by delta E not equal to zero. The symmetry violation field, delta E, represents the first active ingredient of reality. It is not energy in the classical sense, but a measurable deviation from informational balance. The equation shown here describes how these deviations propagate, interact, and stabilize within the informational field. The second-order term captures temporal evolution within the informational domain, while the spatial Laplacian governs how symmetry violations spread across relational structure. Nonlinear coupling introduces self-interaction, allowing perturbations to amplify, collapse, or organize into stable patterns. Finally, the source term represents intrinsic fluctuations, seeding the initial asymmetries. When delta E emerges, information quanta form. These quanta constitute the raw material from which all higher-level phenomena, dark energy, matter, and space-time, eventually arise. Once symmetry violation is present, its effects must be regulated. In the HIQF framework, this regulation is provided by informational pressure, denoted by pi. Informational pressure is defined as proportional to the squared magnitude of the local symmetry violation. In simple terms, it measures how strongly the informational field is stressed by deviations from equilibrium. At the global scale, low and smoothly distributed pressure leads to expansion. This regime corresponds to what is observed as dark energy, driving the large-scale growth of space-time. At the local scale, where pressure exceeds critical thresholds, the behavior changes. High informational pressure causes clumping, stabilization, and condensation. This is the regime where gravity-like effects and matter formation emerge. Informational pressure therefore plays a role analogous to temperature in thermodynamics. Just as temperature determines whether water appears as ice, liquid, or vapor, informational pressure determines whether the underlying field manifests as vacuum, dark matter, or baryonic matter. Different phases of reality are not composed of different substances, but arise from different pressure regimes within the same informational field. This slide presents the spectrum of manifestation within the HIQF framework. All observable forms of reality arise from the same informational field, differentiated not by substance, but by informational pressure. At the lowest end of the spectrum, where global informational pressure dominates, the field manifests as dark energy. In this regime, pressure is smooth and non-local, driving large-scale expansion without forming structure. As pressure becomes locally intensified, but before stable topology emerges, the field enters the dark matter phase. Here, informational density is high, yet no persistent particle-like structures form. With further organization, symmetry violations become oscillatory. These excitations correspond to what is classically identified as energy, dynamic but not permanently localized. Finally, when informational pressure crosses stability thresholds and topology locks in, matter appears. Matter is not fundamental substance, but a stable topological defect of the informational field. In this view, dark matter is not a missing particle. It is a phase of the field, a transitional regime between expansion and structure, governed by informational pressure. In the HIQF framework, spacetime is not a pre-existing container in which events occur. Instead, spacetime emerges as a stabilized subspace of the informational field, selected dynamically by symmetry violation processes. When local informational pressure becomes sufficiently high, the field reorganizes itself into a configuration that minimizes further instability. This stabilized configuration is what we perceive as spacetime geometry. Gravity, in this view, is not the curvature of spacetime itself, but the gradient of informational pressure. Regions of higher local pressure act as attractors, drawing surrounding field configurations towards states of greater stability. What is classically interpreted as mass corresponds to persistent regions of elevated local informational pressure. The gravitational effect arises from how sharply this pressure changes across space, expressed as the gradient of pi local. Thus, gravity is not a fundamental force, but an emergent response of the informational field seeking equilibrium. This slide presents the quantum field formulation of the HIQF framework. Here, the symmetry violation field, delta E, is treated as a dynamical quantum field rather than a classical perturbation. The Lagrangian shown defines the field's behavior through three key components. The first term represents kinetic evolution within the informational domain, governed by an intrinsic propagation speed. The second term captures spatial variation, describing how symmetry violations distribute and interact across relational structure. The final nonlinear term introduces self-interaction, allowing the field to support stable configurations, phase transitions, and emergent structure. Canonical quantization is then imposed through standard commutation relations, promoting delta E and its conjugate momentum to operators. This formalization enables mode expansion, vacuum structure analysis, and path integral methods, directly connecting HIQF to established quantum field theory techniques. Importantly, this does not reduce HIQF to conventional QFT. Instead, it embeds QFT as an effective description of deeper informational dynamics. A central question now arises. If matter emerges from the informational field, why does it not simply dissolve back into it? The answer lies in topology. In the HIQF framework, energy corresponds to configurations with trivial topology. Such states are dynamic and transient. They can freely disperse and reorganize within the field. Between energy and matter lies a transitional regime, where configurations are temporarily organized but not yet topologically protected. These states are inherently unstable and short-lived. Matter, however, is fundamentally different. It corresponds to stable topological defects within the symmetry violation field, delta E. Once such a defect forms, it is protected by topological invariance. Continuous deformations of the field cannot remove it without crossing a critical threshold. In this view, quarks correspond to knotted, topologically stable structures, while dark matter filaments represent non-trivial homotopy classes that lack particle-like localization. This slide introduces the geometric structure underlying the HIQF framework. In HIQF, information is not abstract or dimensionless. It possesses a measurable geometry, described by an informational metric. Here, the Fisher information metric defines how distinguishable informational states are across the field. What we perceive as geometric curvature emerges from variations in informational distinguishability. Within this structure, quantum entanglement is no longer a mysterious action at a distance. Instead, entangled systems share a common manifestational structure within the non-local symmetry violation field. Their correlation reflects geometry, not signaling. Informational pressure maps directly onto relative entropy, quantifying how far a local configuration deviates from equilibrium. Decoherence, in this view, is not a loss of information. It is a symmetry-breaking process where shared informational geometry fragments into locally stabilized structures. Space-time geometry, quantum correlations, and entropy are therefore not separate concepts, but different projections of the same underlying informational geometry. The Hubble tension represents one of the clearest signals that cosmology is probing different physical regimes of the universe. Measurements derived from the early universe, using the cosmic microwave background, sample a domain where local informational pressure gradients are minimal. In this regime, the expansion rate reflects a nearly global equilibrium, yielding a lower value of the Hubble constant. Late universe measurements, based on supernova and large-scale structure, probe a very different environment. Here, the universe is highly structured. Local informational pressure gradients are significant, especially within the cosmic web of filaments and voids. Within the HIQF framework, the locally measured expansion rate naturally increases with the gradient of informational pressure. The equation shown expresses this directly. The local Hubble parameter deviates from the global value in proportion to the ratio of local to global informational pressure. From this perspective, the Hubble tension is not a systematic error or an inconsistency. It is an expected outcome of measuring expansion across different informational pressure regimes of the same universe. Recent observations by the James Webb Space Telescope have revealed a serious challenge for standard cosmology. Massive, well-structured galaxies are observed less than 600 million years after the Big Bang, far earlier than standard gravitational collapse models allow. Within the LI-CDM framework, gravity alone is too weak to account for such rapid structure formation at these early times. The HIQF framework offers a different mechanism. In regions where local informational pressure becomes high, collapse is no longer driven solely by gravity. Instead, informational pressure itself acts as an effective accelerator, amplifying the rate at which matter condenses. The collapse timescale therefore depends not only on gravitational density, but also on the local informational pressure contribution. When this contribution dominates, collapse can proceed orders of magnitude faster than predicted by standard models. As a result, the early formation of massive galaxies is not anomalous. It is a natural consequence of pressure-driven dynamics within the informational field, long before classical gravity becomes the dominant organizing force. A physical theory gains relevance only if it makes clear, testable predictions. HIQF is explicitly constructed with this requirement in mind. In weak gravitational lensing, HIQF predicts that distortions will trace gradients of informational pressure, not merely the distribution of baryonic matter and inferred dark matter halos. This leads to measurable deviations in lensing maps, particularly in regions where mass density alone cannot explain observed shear patterns. In the cosmic microwave background, HIQF predicts non-scale invariant B-mode signatures arising from topological defects in the symmetry violation field, especially at low multipoles. At the particle level, quark masses are expected to cluster around discrete values linked to topological indices, rather than emerging as arbitrary constants. Finally, on the largest scales, the topology of the cosmic web itself becomes a probe. HIQF predicts that Betti numbers describing the connectivity of cosmic structures will correlate directly with informational pressure distributions. Each of these predictions can be independently tested, allowing the framework to be validated or ruled out by observation. This presentation has outlined a shift beyond space-time as a fundamental concept. The holistic informational quantum field provides a single, coherent framework that unifies microphysics and macrophysics under an informational law. Within this framework, dark energy and dark matter are not separate substances or undiscovered particles, but distinct regimes of the same informational field. The Hubble tension emerges naturally from local pressure gradients, rather than signaling a breakdown of cosmology. Space, time, matter, and gravity are no longer treated as primitives. They arise as stable, relational structures formed through symmetry violation, informational pressure, and topology. What appears fragmented across current theories becomes continuous when viewed at the informational level. In this sense, the universe is not a collection of independent objects evolving in a background spacetime. It is a unified field of relations, where structure, dynamics, and observation are different projections of the same underlying informational reality. HIQF does not claim finality, but it offers a path toward deeper unification, grounded in testability and coherence.